Now, this is a problem from the old textbook, Cutnell and Johnson, that cost $250. I used to assign it every semester. A supertanker, mass big, is moving with a constant velocity. Its engines generate a forward thrust of 7.4 times 10 to the 5th newtons. Find the magnitude of the total resistive force exerted on the tanker by the water in the air, and find the magnitude of the upward force exerted on the tanker by the water. Now, every time I assigned this problem, I was guaranteed to have a long line of students outside my door. And nearly every student that walked in my door said the same thing. I have no idea how to start this problem. Well, that's just a lie. You're just looking me in the face and lying to me. Because you know how to start every single dynamics problem. How do you start a dynamics problem? A free body diagram. A free body diagram. Okay, so we draw a free body diagram. The first force we put on it is the weight force. I take that mass that was big, multiply it by 9.8, call it 10, and I get that many newtons. I then ask, are there any magnets in this problem? Nope, they're coming. So what touches the tanker? Well, the water. Now, how do we account for the water? We're told that there's this thrust force caused by the engine on the tanker. Now, if we think about that, that's the engine turning the propeller. And the propeller is shaped such that it pushes water back. Now, if the propeller is pushing water back, by third law, the water is pushing the propeller, and hence the boat, forward. Either way you look at it, it's a forward force that is 7.4 times 10 to the 5th newtons. Now, we also know that there's a force by the water up. That force has a name. It's called the buoyant force. We're not going to get to it before this next exam. We're going to hold off and wait till towards the end of the semester to talk about it. It's one of the most exciting, richest of the forces. It'll be fun. But we don't need to understand it inside out to know how big it is, do we? No, we know how big it is. It's this big. And likewise, in this problem, they lump together all the friction, whether it's due to the water pushing against the front of the ship or the wind pushing against the part of the ship that's out of the water. That's a strange way to lump your friction forces. I wouldn't do it. I don't use their book. Okay? You don't pay $250. But still, without agreeing on that labeling, I know how big this force is, don't I? Because this tanker's going at constant velocity. This diagram has to scream balance. So this force has to be that big, and this force has to be this big. Okay? So it's really not that hard if we just follow the recipe. Now, many, many years ago, when I was your age, if you can imagine it, I took a class from Stephen R. Covey. Now, Stephen R. Covey was the most popular professor on our campus. He went on to become a very famous author, making millions and millions of dollars. There are baseball stadiums that are named after him. And anyway, he was popular because what he would do is he would motivate. And he would motivate by telling stories. And he taught in this great big lecture hall that just went on forever. It was where they had plays and operas and everything. And it was huge, and it was always packed. And he always had 4 TAs that were just in charge of keeping his cable, his cord untangled. Because this was back in the olden days when microphones had cords. And this guy was intense. I mean, his eyes could burn through you. And he's bald as a billiard ball. And he was always just rubbing his head. I think that's how he became bald. And he couldn't stay still. He was all over the room telling his stories. And we were loving his stories. It went on, after he taught for some years, he would give inspirational talks to corporations. And they'd pay him hundreds of thousands of dollars to come in and tell his stories. Well, one story that made an impression on me was a story about a woodcutter. Woompa, 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 sawing down a tree. Woompa, woompa. And along came a hiker, and the hiker said, "What are you doing?" "Woompa, woompa, I'm sawing down this tree." Woompa, woompa. The hiker said, "Whoa, how long's it taken?" "Woompa, woompa, I've been doing it about 6 hours." Woompa, woompa. "Whoa, how come it's taking so long?" "Woompa, woompa, my saw is really dull." Woompa, woompa. "Whoa, why don't you sharpen the saw?" "Woompa, woompa, because I'm busy sawing down this tree." Woompa, woompa. Didn't say it was funny, I said it was meaningful. Now, what does that have to do with you? Next Thursday, on your exam, some of the problems will have boxes where you will draw your free body diagrams. You will be offered lots and lots of points for your free body diagrams. Put the diagram in the box, get your points. Most of the problems on the exam will not have a box for your free body diagram, will not require you to draw a free body diagram. For those problems, you do not, I repeat, you do not have to draw a free body diagram unless you want any hope whatsoever of getting the right answer. Every single dynamics problem starts with a free body diagram. If I don't give you a box, turn the page over, use the back of the page. But if you think you are saving time by not drawing that free body diagram, I've got some trees for you to saw down with my saw. Okay? Now, let's spice this up. Suppose instead of moving with constant velocity, this tanker moves with a constant acceleration. Not a big one, but an acceleration still the same. The mass is the same, the thrust of the engine is the same. If I look at that free body diagram, what has got to change? Yeah, that friction force has to get smaller. Somehow I need to streamline that boat so that either the water's not pushing as hard on it or the wind's not pushing as hard on it.